Hello. So today we have got a bit, probably the most far-reaching or the most like outreaching or complex lecture during this course. We'll be doing something which we sometimes dub LP-guided branching. It's really will be like branching algorithms. We'll be looking how does the solution of the LP relaxation to the problem changes over time, and we're measuring the progress of the branching algorithm by looking how does it affects like how does it affect the LP relaxation for the problem. Okay, so let's just not say something like abstract. Let's go to our favorite problem of vertex cover. This is an example vertex cover instance, and this is a minimum vertex cover in this graph. I hope so. And yeah, we have studied LP. We have studied LP FET algorithms for this problem on the first lecture and then many other lectures. And there's the simple algorithm was to do decay, and we said that we can improve you can improve this algorithm by some mining the branching cases. This is probably the best one, or was the best one a few years ago. I think nothing happened since the few years, but I think this a few years ago this was the best one. And one of the questions we want to ask ourselves today is, well, is the parameter k the correct one? Like if you think about vertex cover instance, the vertex cover graph is usually quite large. So maybe you can actually look at a smaller parameter and look for a vertex cover of like parameterized vertex cover by a smaller parameter than just the size of the vertex cover up there. And that's like one of the questions we'll be pursuing in the next 20 minutes or half an hour. And we studied when we did kernelization, we studied vertex cover, the linear programming relaxation of vertex cover. And this is the simple one. You just put some weights on vertices and you ask the weights should be non-negative, and you ask every edge to be covered by at least weight 1. So the amount of paint on every edge should be at most 1, and you minimize the amount of paint. And on the left, you have a click, and this is this example. Then a click for vertex cover, you need to take n minus 1 vertices if this is an n vertex click, but the vertex cover LP can cheat and color every vertex with half of the paint, with half of the like one half, put one with half, and pay only n half to cover all the edges here. And this is like one of the extremal examples where the vertex cover LP can cheat and pay approximately half of what the integral solution pays here. Okay, so this was what we did. And we had this analysis that I don't want to recall here because it was done on the kernelization lecture. This was one of the first lectures in this course when we actually looked at this vertex cover, solution of the vertex cover LP, and we looked at the guys that got 0, less than half, half, exactly half, more than half, and exactly 1 in the optimum solution. And we said that, well, really, these guys are the problematic guys, and these guys can be assumed to be not in the solution, and these guys can be assumed to be in the solution. Yeah, there was a theorem saying that there exists a minimum integral vertex cover that contains these guys, and this is disjoint with these guys, and this is disjoint with these guys. And we had this analysis. It was quite not that complicated analysis, like shifting around the weight of the solution, proving that is actually the case. So this is so we actually proved first that there's a solution that so we really proved we did this analysis, but in this on the way of this analysis we proved that actually these guys and these guys are not necessary. You can have an optimum solution using only zero empty guys, half guys, and full guys. Okay, and actually there's an optimum integral solution that takes the guys that are more than half or 1, and it covers all the edges incident with the guys that have 0, and you can discard these guys up there. Yeah, that was our reduction. And this reduction, I argued a few times. I mean, we did this reduction only once to say, okay, we leave only half guys, and if now the value of the LP relaxation is more than k, then we can say no. And this was like this 2k vertex kernel, 2k vertex kernel for vertex cover that we did in one of the first lectures. But I told you at that moment that you can actually assume that the LP that you can get the instance when the unique optimum solution to the LP is like all halves, that you cannot reduce anything. And I told you that, okay, you can solve the LP, but you can also solve the LP with some like extra constraint, like this vertex is 0, this vertex is 1, and see if the minimum value of the LP relaxation changes. And this manner you can poke around and check if there exists an optimum LP solution that doesn't use all halves. And if there exists, then you can do some reduction according to this theorem we have. So you can end up with the situation that the all halves is the unique LP optimum. There's no other LP optimum apart from like giving half to every vertex in the graph. Okay, and we said, okay, this is fine. We have got our 2K vertex kernel. That was fine for us in the first lecture, but now we want to do something different. Now we want to say, hey, let's now take a vertex and branch on it. Okay, and so by reduction rules, we can get to the point when all halves is the unique LP's optimum, and take a vertex and branch on it and see what happens. And okay, so branching for vertex cover is taking a vertex in into the solution, taking all the neighbors into the solution. Okay, and taking a vertex to the solution is really the same as adding the constraint xv equals 1 to the LP. It's like you need to pay 1 for this vertex. I mean, you need to pay 1. I mean, this is like you can actually delete this vertex and decrease the budget by 1, or like account 1 for the costs, but you can think of it as like forcing this vertex to be value 1 in your LP solution. Okay, and now look that since all halves was the unique optimum, if we are forcing this vertex to be 1 in the LP solution, we no longer can have an optimum. Okay, but this corresponds to the case when we actually delete this vertex and look at the remaining graph. So the remaining graph has an optimum that's half integral, that uses only zeros, halves, and ones. Okay, so once we force this one, there's again an optimum that uses ones, zeros, and halves, which means that this value of this LP needs to go up by at least half. Yeah, because it cannot be an optimum, and it's like it cannot go continuously. I mean, it can assume there's an optimum that assigns only values zeros, halves, and ones. So actually, the LP value needs to go by half. So what happens here? You can think of the following: K stays for a moment the same. You force this guy to be 1. The LP goes up by half, and then this 1, you actually delete them and decrease K by 1, and the LP decreases by 1. Okay, this reduction. So as a result, you can think of this excess. If you look at this excess, I mean, how much more? So the LP is a lower bound for your solution size, for integral solution size. You can look at the parameter, what's the slack, how much slack you have on top of the LP, how much extra you can pay for integral solution on top of the LP lower bound here, okay? And the observation here is that this difference goes down by half in this branch, because the K stays the same and the LP go by half, and then you have got this vertex of value 1 and you deleted them, so both LP and K decreases by 1. So the difference in the end decreases by half. Okay, something, but let's look at the other branch. In the other branch, we are saying, okay, V is not in the solution, which means that the neighbors of V are in the solution. This really in the LP business corresponds to like adding a constraint. This vertex has got value 0. This will force the neighbors to be 1, and the neighbors will get deleted, and then maybe and the rest of the graph will be resolved as a normal LP, a normal vertex cover instance. Okay, and the observation is like we have got exactly the same analysis as before. We had got all halves to start from. We had all halves to start from, and then we like punched away from this unique optimum. Okay, we said, okay, but this guy needs to be 0. And now the neighbors get 1, and all the other guys get another solution, and we use again our theorem that there's a few solution using only zeros, halves, and ones. So the global LP value needed to go up by at least half by forcing this guy to be 0. Okay, so we have got again the same analysis. We add some forcement, and the LP went up by half. K stayed the same, and now what we did, we take it all ones or guys with value 1 into the solution, and that decreases, every such guy decreases the LP by 1 and decreases K by 1. So this keeps the difference the same, which means that in this branch also this excess over the LP value decreases by half. Okay, so this is an excellent measure. We have got a branching that has got branching factor 2, and in both options, some measure, the excess over the LP, K minus LP, decreases by half. Okay, so we end up with a theorem saying that actually if this problem can be solved in like, I mean, you have got two-way branching. At every step this K minus LP decreases by half, so you have got 4 to the K minus LP branching algorithm. Yeah, 2 to the twice K minus LP. Okay, so this is the algorithm up there, and you get there. And yeah, so this is like quite simple. It was very surprising when we observed it that they actually get this simple algorithm. You look at the tutorials with Wojtek on some corollaries that actually this problem like vertex cover above, with this parameterization above LP can actually capture a number of other problems. But shortly after we observed this once, another team came and said that actually this is a standard branching, so you can mine some cases. Okay, let's look at this branching and try to analyze which case is the worst. So if you take the vertex into the solution, that looks quite hopeless. You take this vertex into the solution, it gets value 1, the LP goes I by half, and that's it. Nothing more happens really in most of the cases. Yeah, so that's bad. But maybe you can get more from the case when you force the guy to be 0, because that seems like the more, I mean, you get more progress. If you don't take these guys into the solution, or the neighbors come to the solution, and maybe you can get more progress here, okay? So let's analyze the worst case when actually forcing the guy to be 0 increase the LP only by half, okay? So how does it work? You take some guy, maybe this is this guy, and what does it really work? It will, okay, it will take the neighbors to be 1, it will take the neighbors to be 1, and then it will resolve the vertex cover LP on the remainder of the graph, okay? And this is not necessarily all halves anymore, yeah? It can be zeros here, it can be put some zeros here, and put some ones here, and the rest is 1/2, okay? So what it really does, it puts some independent set, on some independent set it puts zeros, on the neighbors of the independent set it puts ones, and the rest it puts halves, and it looks for a minimum cost such solution such that your favorite vertex V, that your branching pivot, is in the independent set sites, is on the independent set sites. So forcing this guy to be independent set guys in this in this picture. Okay. So now what does it mean that so originally everybody got halves. Okay, originally everybody got halves, and now we are forcing this guy to be 0, and now everybody what happens is that now the LP solution went up by only a half. What does it mean? Okay, originally it was all halves. Now we have got this picture of zeros, ones, and halves, but the total value went up only by half. That means that if there are like L guys here, then there are L plus 1 guys here. Yeah, the number of ones is larger by 1 by the number of zeros. By this manner, you get like half more cost than you had before. Okay, so this picture was that this picture needs to, if the LP increases only by half, then this picture needs to be like independent set containing V, that whose neighborhood is one vertex larger, Okay, so we have got this picture. Let's move on. Okay, this is the calculations here, and now, okay, now in this picture, we have got this picture that there's L guys here and L plus 1 guys here, and we can again repeat our analysis from the LP branch, from the our analysis from the vertex cover LP that we had, that actually every guy here, so let's call this is the 0 part, V0, every guy here needs to have got more neighbors than its own set. Every independent set needs to have got more neighbors than its own size. Otherwise, you could put zeros here, half 1 here, and half everywhere here, and have another LP optimum. Yeah, I mean, this is like the analysis we had. If all halves is the unique LP solution, then every independent set has got larger neighborhood than itself, because otherwise you could put zeros on the independent set and ones on the neighbors, and this is at least as good as putting halves everywhere. Okay. So this is the first observation we have. So what do we have? So we have got like a Hall's theorem here. We have got Hall's theorem here with a slack. Yeah, there's a strict inequality here. Okay, every set on the left has got strictly larger neighborhood. Okay, which means that if you take any guy here and like hide this guy for a moment, there is still a perfect matching between zeros and ones. Okay, this is like this applying Hall's theorem. Like if you delete any guy from the V1, from the full guys, then still this inequality becomes soft inequality. I mean, not a strict one, because there's one guy hidden from the neighborhood, and you still have got Hall condition, so you have got a perfect matching. So you have got the property that whatever guy you kill from the V1, you still have got a perfect matching from left to right, which means that even if there's L guys here and L plus 1 guys here, and if you take one guy to the solution, you still need to take L guys here. Okay? You still, I mean, if one guy from here is in the solution, you still need to take L guys from here. So as well, you could take one of these guys. So as well, you can take all these guys, yeah? So what I'm just saying here is that if there is a guy that's taken to your vertex cover, then omitting this guy, you still have got a perfect matching between zeros and ones. So you need to use at least L guys in this part of the graph. So you could as well take the entire V1 part. The other option is that you don't take any of these guys to your solution, to your vertex cover. Okay, that means that you need to take all these guys, yeah, because this was the neighborhood of the zeros. The ones are the neighbors of the zeros, which means that all these guys needs to be in the solution to cover the edges in between. Okay, so the punchline here is that okay, that was the first sentence, that if somebody is in the solution, then we can greedily take the entire V1 in the solution. Yeah, this is V1 and this is V0. Okay, otherwise, there's an option of like taking nobody from here and everybody here. Okay, taking all these guys and nobody from here. Okay, but this can only be possible. This is only possible if there is no edge here in between. Yeah, if you can really afford not taking, if it's feasible to take nobody from V1. Okay, so what's now the punchline? Let's now go to the end. If inside V1 there's some edge, then you can greedily take the entire V1 into the solution. Because of this edge, one of these guys needs to be in the solution, then in the vertex cover reconstructing, but then there's a matching left, and that means that you need to pay L here, which means that as well you can take the entire V1. Okay, so if there's an edge inside V1, you just greedily take V1. Otherwise, you don't know what to do, but there are really two options. Either take somebody from V1, and then you can as well take everybody from V1, or take nobody from V1, but then you need to take the entire V0. Okay, so this behaves as follows. Either you pay L and take the entire V0, but then V1 stays, and it's still like present in the graph, and all these edges going up here are still present in the graph, or you pay one more, pay L plus 1, and take the entire V1, and then get rid not only of V0, but also all edges going to the rest of the graph. Okay, so this is like really like a picture that has got two options. Either you pay L and only get rid of the edges incident with V0, or pay one more and get rid also of all the edges going to the rest of the graph. So what I'm just saying here, what I want to say now is that this is exactly the same as contracting this everything to a single vertex. Like a single vertex with all the edges that were before, this has exactly the same behavior. Either you pay 0 and don't delete this guy, but you have got to take care of these edges, or you pay 1 and take this guy into solution, and then you don't need to care about the edges going to the rest of the graph. Okay, so I want to say that there's the reduction that just contracts V0 and V1 into one new vertex and decrease K by L. And decrease K by L. Yeah, because instead of options L and L plus 1, you have got options 0 and 1. So your budget decreases by L. And also note that the size of the LP solution decreases by L because you deleted 2 L vertices in there. I mean, you replace it 2 L plus 1 vertices with one vertex, which means that if you put half here, this is really I mean, you can prove that this is actually the optimal LP solution putting half here in this picture. Okay, so we have got a reduction. The point here is that we have got the reduction that if I have got an independent set whose neighborhood is one size larger, I have a reduction that gets rid of some vertices and actually preserves the gap K minus LP, which I haven't proved formally, but you can follow it. It's easy to prove it. Okay, so I have got a reduction. So whenever we have got this branching, and actually in the force xv equals 0 case, we actually have got LP only by half. That means that we have got this picture, and we, instead of branching, we could have used the reduction. Okay, so so we can get this assumption that for whenever there's an independent set, the size of the neighborhood is at least twice larger, because if we encounter one larger neighborhood, we can do a reduction. Okay, which means that this worst case branching cannot happen. In the branching on the left side, when we take a vertex in the solution, we cannot do anything. We just take this vertex, delete, the gap between K and LP gets down by half. But in the other branch, every independent set has got neighborhood at least twice larger, so it cannot happen that the LP goes only by half. Okay, it goes by at least 1. Yeah, because I mean, there's the granularity of the LP value is halves, so it cannot go up by half. It needs to go up by 1. So we have got better branching. There's either decrease by half or decrease by 1 in the branching. And that means that you have got a better Bayesian analysis, and you get like called 1 plus Kelvin ratio to K minus LP matter. Okay, so you can mine these cases, and actually there was a paper, I mean the same paper in the journal version with Daniel Okshanov on top of it, actually noticed that you can mine cases more, and they got 2.3 something something. This is like a complicated case analysis there. And the other observation is that this problem, vertex cover parameterized LP, actually is a general problem that captures a number of problems. And I think Wojtek during tutorials will discuss with you how to phrase odd-cycle transversal and almost two-sat as a vertex cover above LP, how to reduce one to another and actually prove it using this one. So odd-cycle transversal is something, as you may recall, there was this classic iterative compression flow algorithm that Michał presented to you that was free to decay for the cycle transversal. And this is actually a way to get better than free to decay. So you can actually get 2.315 to decay for odd cycle transversal by these tricks, by this type of tricks, and which was quite surprising at the time. And I want to mention that it's still open to get down to 2 to the something to improve. I mean, this is like complicated case analysis. The intuition is that maybe 2 to the should be possible here, but we don't know how to do it. So it remains open. Okay, good. So this was vertex cover. We didn't do anything really complicated here. We based ourselves really on the analysis of the vertex cover LP we had before, and this very strict property that you have got not only zeros, halves, and ones. It's not only half integral, but also that you can greedily take ones and discard zeros in the instance. So there was some sort of persistence that if the LP says this is 0, this is 1, then you can fix these decisions for the integral, and that would be fine. Yeah, so we had these two properties. We have got the half integrality, and we have got this persistence that allows us to fix the decisions of the LP for the integral solution as well. Okay, and you may ask the question, in which other problems we have got LP relaxation with these two other properties? And the answer is actually multi-way cut. As you remember, there was the problem of multi-way cut when you have got terminals and you want to do the vertices or edges to separate terminals from each other. And there's an observation that actually vertex cover is a special case of multi-way cut, because if you have got the vertex cover instance, you can attach a terminal to every vertex. So I attach a terminal to every vertex, and now you can observe that actually a solution to the vertex cover is the same as the solution to the multi-way cut, to the node multi-way cut, node deletion multi-way cut, because I mean, you really need to kill every edge of the original graph to cut the connection between the two neighboring terminals. Okay, so this is an easy reduction, and actually I proved that multi-way cut with many terminals is NP hard. You may, I mean, I told you last time that is even hard for 3 terminals. This is more complicated reduction. This is an easy reduction that not multi-way cut is hard for many terminals. And you can also write an LP relaxation for multi-way cut. And as we will discuss in a moment, it will have got very nice properties. So instead of the vertex cover LP that says, hey, kill all, I mean, cover all the edges with weight at least 1, with at most at least 1 paint, I will use the following. I'm again painting vertices, but now I want to say that every path between 2 terminals, 2 different terminals, needs to see at least 1 paint. Okay, so this is like the same like obstacle hitting LP that is present in many scenarios. Okay, we don't like paths between terminals, we want to destroy them, so we want to put weights on vertices so that every object we want to destroy has got total weight at least 1, and this will be like a relaxation of the multi-way LP. Okay, good. So before we analyze this LP, which is slightly more complicated, and we won't actually analyze it in full detail, I want to look back into, okay, sorry, that was wrong. I want to look back to the edge variant, because the edge variant doesn't require the LP for this analysis to hold, and it's actually quite insightful here. So instead of doing node, which we discussed last time, that you want to delete vertices, now I want to delete k edges to separate the terminals from each other. And this will be slightly easier in the sense that you don't need the LP to do what we'll be doing in the next 15 minutes. Okay. So this is the edge multi-way cut, and let's go further. So on the picture, we have got 3 terminals, and you want to cut some edges to separate the terminals from each other, and you want to cut the terminals as little terminals as possible. a little edge as possible to separate terminals from each other. Okay, and now the first observation is that, okay, let's assume that the graph is connected. I mean, you can just do every connected component separately, it's not a problem. And in this manner, if you look at the optimum solution, the minimum solution, then every edge really connects two areas from different terminals. Yeah, every edge is necessary for the solution, so you can really get from one terminal to edge of the solution, go there and go further. Okay, so that you really, I mean, you need every edge. Okay, so the observation is that actually, well, yeah, so this is like what we want, and what I want to say is, okay, that's I want to skip the slide that we're doing here, but I want to say the following is that last time we had this reduction that was present for multi-way cut, which was present, we proved it in the Vertex version, but in the EDGE version, the proof is exactly the same, that if you look at one terminal, and you try to separate this terminal from the rest of the graph, from the remaining terminal, so this is t minus t, then there's this space of minimum cuts, and you can take the furthest one, there was the furthest one, the ones with inclusion-wise minimal reachable set from t, and you can actually prove that, I mean, in the vertex deletion variant, it was that nobody from here is deleted. You can contract this area onto t. In the edge deletion variant, this boils down to like no edge inside here is deleted. I mean, all the edges, I mean, the solution is entirely here. So that you can really, again, contract this area onto T, okay? And so you take this min cut as furthest from T and you contract the reachable from T part onto T, and that won't break the solution because we proved, that was a simple proof using some modularity last week, that actually this, I mean, you can always like move the solution away from this area reachable from T here, okay? So let's do this reduction, yeah? So this was the dilemma we actually proved last time, that there's in the Vertex version that there is an optimum solution to the instance that doesn't include any edge with both endpoints in this reachable area here. Okay. Both endpoints in I is okay. It's like min cut means the reachable area. Sorry, there's like the reachable area here. Okay. Okay, so we contracted, there's some back with the slides here. So we actually can contract this one, this area here that was here onto this terminal, and actually, I mean, reduce this area to a single vertex. So what you end up with the picture, and you can actually have a second, the obvious reduction that if there's an edge connecting to terminals, you just delete this edge because it needs to be in a solution. Yeah, that's like the obvious reduction. An edge connecting to terminals needs to be in the solution. So this is the second reduction rule. And if we apply these rules exhaustively, we actually end up, actually with this picture up here that actually every terminal, its minimum cut from the rest of the terminals are in incident edges, and there are no edges going between terminals. So there are no such edges going between the terminals up there. Okay, so these edges incident with the terminals are disjoint, and these are the unique minimum cuts between the terminal and the remaining terminals up there. Okay. And now the observation is that, okay, so let's look at the solution here. Let's look at the solution here. Yeah, okay. So what we have the first observation we have here is that if you take any other setup here, then the number of edges here is actually larger than the number of edges here. Yeah, because that was the unique minimum cut. So if you take any other cut between the terminal and the remaining terminals, you have got a larger cut. Okay. And the other observation is that, hey, let's look at the solution. So this is a solution here in this picture. And let's count how many edges this area sees. So like how many edges are visible from this terminal. So this is T1, how many edges are visible from this terminal. And take terminal 2 and count how many edges are visible of the solution are visible from this terminal. And take terminal 3 and count how many edges are visible from terminal 3 from the solution. Okay. And let's di be the number of edges reachable, like this is like the reachable number of edges of the solution reachable from the terminal I. And the point is that if you count this, if you sum the i's, this will be twice the size of the solution. Yeah, you will count every edge of the solution twice. This is the moment when we are using the that we are cutting edges, not vertices. So far, everything I said was true also for vertices. Now we are using the fact we are cutting edges. Every edge is counted exactly twice. Okay, from the two endpoints here, because we're looking at the minimum solution that doesn't delete its edges without a reason. Okay, so we have got this observation. So and obviously all these di's, this is like a minimum cut, this guy, di, this set is minimum cut between a terminal and the rest. So you always, like this di is at least the number, the ci, which is the number of edges here, this is ci. Yeah, the number of edges here. So yeah, so you have got like this DIs needs to be at least CIs, and the total solution is half the sum of all DIs. Okay, so cutting all these terminals away, we actually proved that cutting all these terminals away is a two approximation to the problem. Yeah, we proved that this is a two approximation to the problem. Well, because if you cut all these guys here away, you pay sum of CI, and this is smaller than sum of DI, which is smaller than twice the optimum solution. Okay, so like after doing these reductions, cutting away all the terminals from by cutting its incident edges, this is a two approximation to the problem. And actually, you can observe that you can cut away all but one terminal. Yeah, you can avoid. So this is like sum of CIs minus one CI. So you can skip the largest CI. So you can actually have got something like 2 minus 1 over T approximation to the problem, because you don't you can skip one of the CIs in the sum. Okay. Okay. So yeah, so this is what I said. We got the approximation, but that doesn't really bound. Let's look at this lower bound, or this like twice the lower bound. So we have got that the sum of CIs is smaller than the sum of DIs, which is twice the size of F, which means that the size of F is at least sum of CIs half. Okay, at least sum of CIs half. Okay, so the number of edges instead of the terminals after the reductions half is a lower bound on the solution size. It's a lower bound on the solution size. Okay, and we will try to actually see how does this lower bound change just in the branching. Okay, and what I would like to convince you in a moment is that actually this will behave exactly the same as in the vertex cover case. That this would be exactly the same as the vertex cover case. Why would it be so? Okay. Okay, this is like the analysis we had just before. So yeah, I want to say here is that we'll have exactly the same as in the vertex cover says, that we'll be taking an edge incident with the terminal and saying either it's in the solution or not. If it's in the solution, we'll be deleting it. Okay, but the only one CI will be decreased by one, which means that like this lower bound will decrease only by half, but our budget will decrease by one. And the other option will making it undeletable, so we'll be contracting this edge really onto the terminal, and that will increase one of the CIs, and that will also make some, that will also like increase the lower bound here. So we have got more or less the same analysis for the vertex cover, but let's go over it in some detail. Okay, let's go to this. Okay, so we'll be looking at this potential, which is like, okay, we thought previously of k minus this sum of CI's half. We'll be looking at twice this was. Yeah, so we'll be looking at twice this. Yeah, so this is our budget for deletion. This is our lower bound. So we're looking at the excess above the lower bound, and it will be easier to look at twice the excess, so that our decreases are integral. Okay, our decreases are integral. Okay, and on trivial, I mean, okay, and if our okay, if our lower bound is exactly equals k, then you can actually observe from the previous analysis that I mean, you need to cut all but one CIs. The smallest CIs is like the only reasonable, because the CIs needs to equal DIs, and so you need to cut just near the terminals, and then the instance should be trivial. So yeah, so let's assume that this excess is above 0, and yeah, so we apply our reduction rules. I mean, we end up with this situation that, okay, there are no edges between terminals, and the minimum terminal to the remaining terminals cut is just the incident edges up there. Okay, and now we, as I said, we branch into two cases. We take an edge incident to terminal and branch into the cases. So we either delete this edge and decrease the value of the solution by 1, or we actually contract this edge and don't change anything more, just contract this edge, and we see what happens. Okay, and let's now take the next few cases, the next few slides, and let's analyze these cases in more detail here. Okay, and okay, the punchline is that, okay, we'll do like in the branch, after branching in the next recursion, we'll again apply reductions, apply reductions branch, and stop when actually the lower bound exceeds our budget. Then we say, okay, there's no solution because the lower bound is larger than our budget. Okay, good. So let's look at the branch when we delete the edge. Okay, and let's recall that we are looking at this twice k minus sum of CI's half. Okay, this is sum of CI's. Okay, so we delete this edge. What happens there? Okay, k gets decreased by 1. Okay, k gets decreased by 1. This we have got this terminal t that we delete this edge ut. Okay, and there are other terminals up here. There are other terminals somewhere there. Okay, this edge gets decreased. So the point is that the mean cut gets decreased by 1. Yeah, I mean this was the mean cut, and we delete one edge from the mean cut. So this remains the mean cut. So this mean cut still gets decreased by 1. So the mean cut here gets decreased by 1. The other observation is that the other mean cuts don't change. Okay, let's draw this picture again. So this is our instance. Say there are 3 terminals, and we delete one edge here. We delete one edge here to the u, and this is an edge this is not a terminal. This is important property of the second thing. This is not an edge towards terminal. And recall that we had that this edges was the minimum cut, the unique minimum cut between this terminal, say T2 and the other terminals, and this edges here were the unique minimum cut between T3 and the remaining graph. And now the point is that deleting this edge here, so taking a red pen and deleting this edge here, this won't make this minimum cut smaller. Okay, this edge was not part of any minimum cut between T2 and the remaining graphs, because that was the unique minimum cut. Maybe by deleting this edge, maybe another minimum cut will appear between T2 and another ones. Maybe there will be more minimum cuts and the reduction one will actually kick in and do some reductions. But so far, we didn't decrease the size of the minimum cut because that was the unique one and we did some other edge. Okay, so if you have got a unique minimum cut and you delete some different edge, which is not in the minimum cut, you don't change the size of the minimum cut. Maybe it will no longer be a minimum cut, but you won't decrease the size of the minimum cut. Maybe it will no longer be the unique minimum cut, but it will still be the minimum cut. Okay, which means that one CI will decrease by 1, the one incident with T, and the other guys will stay the same because we're not deleting any edge of a unique minimum cut for other terminals. Okay, which means that the sum of CIs decreases by 1 and K decreases by 1, which means that the potential decreases by 1. Okay, yeah, because K, I mean, you can think of K minus sum of CI half, that this decreases by 1 and this decreases by half. So the difference decreases by half. Okay, so this is like, so we can think of this, okay, our budget decreases by 1, but our lower bound decreases only by half. So the excess decreases. So the excess decreases by half. Okay, so this picture, yep. And in the other direction, if this edge is contracted, this is actually a simpler one because K stays the same. And the point is that the minimum cut from this guy increases and the other cannot decrease. And the other guys cannot decrease, stays the same. I mean, if you contract an edge, you cannot decrease the size of a minimum cut. I mean, this like if you contract an edge, cutting is even harder. So you cannot decrease any CI, and actually the one from T gets increased, but because you contract an edge of the unique minimum cut. Yeah, so you can have got sum of CIs gets up by 1, K stays the same, K stays the same, so this decreases by, so this decreases, the excess decreases by half, or this phi decreases by 1. Okay, this is like very similar to what we have here. So we started with potential being 2K minus the sum of CIs. This was our potential phi, which was at most K because the sum of CIs because the sum of CIs needs to be it's the lower bound on the solution size. Because if the sum of CIs is smaller than K, then we just delete all the incident guys and say yes to start from. So the sum of CIs needs to be larger than K. Otherwise, we have got a trivial solution. Yeah. Otherwise, we have got a solution. So this is at most K. And we have got, so we ended up with 2 decay algorithm for edge multi-way cut. Okay, we ended up with 2 edge algorithm for 2 multi-way cut. This is better than what we had previous time because, okay, we have got the potential. This was this phi, which was 2K minus sum of CIs. It starts with something at most K, and then every step it decreases by 1. Yeah, you can also think, I mean, the other way of thinking is that you have got this excess sum of CI half, because this is a 2 approximation, this excess starts with at most K half and decreases by half in every branch. So we have got 2 decay algorithm. This was actually observed first by Xiao a few years back, this algorithm. And yeah, so you have got a better algorithm than we had before for edge multi-way cut. Okay, this was edges. Okay, and the point was like, this was again the same progress as before, like, okay, deleting an edge is usually some progress because you decreased K, but contracting an edge was a progress because our lower bound increases. Our lower bound, the sum of CIs increased, and that was the progress here. Okay. So let's try to, so there are two things I swept under the rug during this destruction. The first thing is that I at some moment said about connected graphs and then started deleting edges, so this can be disconnected. But actually, I described the action for connected graphs, but actually I split into connected components separately and everything goes smoothly. There's no problem here, it's just like a syntactic problem. It's like a fake problem here, okay? The other problem is that you need to check that the reduction rules do not decrease the potential, do not increase the potential. Because if the reduction rules again do something wrong with the potential, the analysis goes haywire. This is a problem, but actually don't. You can actually analyze you can actually analyze that. Okay, you're actually doing only contractions. Delete the edge that's obviously in the solution, and that's that simple part. This is the second reduction rule, and the first one, you only contract, so the CIs only go up. So you cannot break the potential by contracting some edges in the graph. Okay, and the second rule says, okay, CIs, by deleting an edge between two terminals, you decrease k by 1, and you decrease two CIs by 1, and so the potential stays the same. The potential stays the same, so that's not a problem. Okay, so now we want to do it for node multiway cut, and this is from the same paper as before I told you. That actually you can do this also for the vertex case. And so we were using edges, and there was one very critical moment when we were using edges, when we said that, okay, every edge is seen twice, so the sum of CI's half is a lower bound for the solution. And this is no longer the true for node multiway cut. You're looking, obviously, instead of edge cuts, you want to look at vertex cuts. So you want to look at the minimum cut separating a terminal from the remaining terminals. And as we, from our analysis from the previous lecture, you can actually contract everything before onto the terminal and have that the neighbors of the terminal is the unique cut between the terminal and the other terminals. So you can get here. The problem is that you no longer have this two approximation. Yeah, you can have this picture that actually there are many terminals around, and there's one common neighbor, and this neighbor is actually a minimum cut between any terminal and the other terminals. So like the CI is always 1, but like the solution is of size 1, yeah, and there are many terminals here. So so like a terminal from the solution can see many different areas of different terminals, so it can be counted many times in the sum of like the boundaries of the areas of the terminals here. Okay, so that's the problem. Yeah, that was the picture I drew. So we need a smarter lower bound, and this is the moment when you come back to the LP solution. This is the one when we come back to the LP solution and say, okay, we did some home-brewed analysis of edges in the previous thing, and now the point is that if you look, instead of just trying to do something again homebrew with the cuts, you actually want to look at the LP relaxation. Okay. So just to recall what we did quickly a few slides ago, there is, so we have got like, so if you want to write node multiway cut as an integer program, so let's say not relaxation, but integer program, you have for every vertex a variable if you take it or not. Okay, if you take it or not, and you want to take as little as possible vertices, as few as possible vertices, and you want to separate all the terminals. Yeah. So for any power between two terminals, you want to hit it. You want to take at least one vertex from this path. And now you are relaxing this thing to a linear constraint, which means that every vertex can be taken in fraction to the solution. So there can be some weight put or like some amount of paint. And on every path, the total amount of paint or the total amount of weight needs to be at least 1. Yeah. So this is the relaxation. And of course, it's a relaxation, so it doesn't provide an integral solution always. Because, for example, you can reduce from the vertex cover and do this click with attached terminals to every vertex, and then this relaxation will put half of every vertex on the click, but you need almost delete the entire click in the integral solution. Okay. So this is our relaxation we're going to look at, and note that this solution, this linear relaxation, has got exponential number of constraints, so you cannot really write it. Yeah, but there's this like way that also is discussed in the algorithmic course and many other courses, that actually like to solve the LP, you actually need an oracle. You don't need to list all the constraints, but you need an oracle that points you to an unsatisfied constraints so far. So now if you have got some weights distribution, finding a path that's not hit path between terminals that has got weight less than 1 is just some simple variant of the shortest path algorithm. So this is not a problem. Separation oracle is not a problem here. Okay. So we have got this ones, and now we open. Okay, so now we want to understand what's the properties of this LP relaxation, and this is a bit beyond the scope of this this beyond the scope of this lecture or this course. This is really like from analyze FP that you need to. It's not a very difficult proof, but you need to play for a while with like primal dual complementary slackness, which is something we're training you in basics on the Logarithmica course. So I decided not to do it here because it's not really the topic of this course and you need some fluency with this slackness condition. So it will take me like half an hour to be everybody on the same page with the slackness condition. Some of you attended the Logarithmica, some of you didn't. So I want to skip this ones. But what I want, the punchline here is that actually there is an LP, there's a half integrality property, that there's a solution that uses only zeros, halves, and ones. Okay, this is, and if somebody is interested, you can try to Google the paper that contains it or look into the Varzirani's book on approximation algorithms in chapter 19. There, at least Micha wrote it on the slides, so I hope it's true. Okay, yeah, so and the problem point is that you actually can find the solution, half integral solution in polynomial time, which is not, I mean, you can actually use self-reducibility and actually like use the fact, I mean, it's not really difficult once you understand why it's half integral that you can actually find a half integral solution there, okay? So this half integral solution is obviously to approximation because, okay, somebody gives you this solution and you can just round up all halves to ones, you overpay by at most twice, and you have got an integral solution. Like every path had weight 1 before, so between terminals and it's 1, so now the more, so you have got integral solution of size at least twice the LP. So your LP is at 2 approximation, okay, because it's half integral, okay? So now let's now analyze this half integral solution because apparently it will have got quite a special structure here. Okay, so let's take a half integral solution. Okay, this is some node multiway cut instance, and let's take that and let's look. So half integral, so it uses only zeros, halves, and ones. Okay, so let's take a terminal and let's look where you can go going over all any vertices of value 0. Yeah, so think of the 0 result. Take a terminal T, and you got which vertex you can reach going only over vertices of weight 0. This will be a 0 region of a vertex. Okay, so you're starting from a terminal and you're looking who is reachable within weight 0, and these regions will be disjoint. Yeah, these regions are disjoint because you cannot go from a terminal to terminal without cost at least 1 on a path. Okay, so they're like just 0 regions. They're like the counties of these terminals up there. Okay. And the observation is that, okay, on the boundary, you have got at least halves, yeah, because the solution uses only zeros, halves, and ones. You define this as everything you can reach with cost 0 from a terminal. So on the boundary, you see halves and ones, okay? So if there's a vertex like this one, that is on the boundary of 2 different regions, you need to have ones here, okay? You need to have ones here because, I mean, there's a path that goes there and goes there, and this is the only vertex of positive weight, so it needs to have got weight 1. Okay, the same, this vertex is here. The other observation is that, okay, but there will be some areas that are like not, they're not in no 0 regions, but are also like not on the boundary on a 0 region, okay? And the observation is that, okay, you can take halves everywhere else, okay? So I want, let me be formal, okay? I take any half integral LP solution, optimal LP solution, okay? I look at the 0 regions and I look at the boundary of the 0 regions and say, okay, the LP solution must put ones on the guys that are on boundary of 2 0 regions or more 0 regions because they are just the unique vertex with a weight on some terminal path. But there are also vertices that are on the boundary of only 1 0 region, okay? And I want to say, if I give only half to these guys, then this will be a valid solution for the node multiway cut. So the claim is as follows, okay? If I put ones on the guys that see 2 0 regions and halves on the guys that see only 1 0 region, then this is a valid solution, yeah? Because any terminal to terminal path needs to start with the 0 region and leaves this 0 region. If it leaves by a 1 vertex, it's hit. If it leads by a half vertex, then from the other endpoint of the path, it needs also to hit a half vertex and a different one, because this guy neighbors only one zero region. So this other guy needs to be another guy that neighbors another zero region. Okay, so on every path, you either leave two different zero regions on two endpoints, so you score at least two halves, or you actually go between two zero regions by one vertex, and then these guys have one. Okay, so you can look. So if you're looking at any half integral solution, you can define zero regions and say, hey, by putting halves on the boundaries of zero regions and ones if there's a guy that sees two zero regions or more zero regions, then you have got the optimal solution. And so if you start with the optimal solution, this is what you need to see. I mean, this is this solution you're looking at, because this is enough and this is necessary. Yeah? It needs to be halves here and needs to be ones here. Okay. So what we have just proven is that any optimum half integral solution has got this structure that it defines zero regions around every terminal and then puts weights on the neighbors of zero regions, halves on a neighbor of one zero region, and ones on the neighbors of two or more zero regions. Okay, so this is like this structure of the structure of the optimum half integral solution that we have proven here. Okay. Okay, this is like a formal proof here. So this is the lemma here that, okay, this is what I said before. Yeah, you put ones if you're neighboring two zero regions or more, or half you're neighboring exactly one zero region and zero otherwise. And this is the structure of any optimal half integral solution. Okay. And now I want to prove the following things, which was observed by Guillemot a few years back, that actually you have got the analog of the reduction of the minimum cut reduction. So in the edge cut, you have got the furthest minimum cut, and then you contracted the thing on the terminal. And now there's the observation, which is like quite complicated. I mean, it's more complicated than the previous one, because the zero region may be larger than up to minimum cut, is that actually the zero region can be contracted onto T. That means that there's a solution disjoint with a zero region of it. There's an optimum integral solution which is disjoint. So let's try to prove it. This is really like shifting. So let's look at this picture. On this picture, this blue guys, I believe, the blue guys is the solution, and the yellow guy is the zero region, and there are these halves on the boundary. Okay. On this picture, I'm assuming that there are no ones. It's not very difficult to adjust it to using ones. It's just a bit more technical, so I'm not proving it fully details. I'm assuming that the boundary is just all halves. There are halves here on the boundary. Okay. And now I want to say that, okay, well, say that the solution does this once. Okay. And what I want to do, so let's look at the guys that are inside here. Yeah. Let's look at the guys that are inside here, that are inside this zero region. I want to get rid of them. I want to push them away from this area. I want to say, okay, you can as well use something else instead of these guys. Okay. So, okay. So now in this picture, there are these guys, which are the color green. There are these guys here, which are separated from the terminal inside the yellow region. Okay. So this is that, okay. So these are the guys that are in the half integral solution. There's some weight put in this half integral solution here, in this half integral solution. But the integral solution I'm looking at, the integral solution X I'm looking at, separates them from the corresponding guy from this corresponding terminal. Yeah? These are the guys that are cut away from the corresponding terminal by the solution. Okay, so that you cannot go within the zero region without going into the solution. Okay, and now what I want to say is that, okay, I could do the following. I can, from my solution, I can not use these guys, but use these guys. Okay, I could use as well these guys instead of the other guys. Okay, and you need to check two things. I mean, yeah, so you need to think this was, and you want to say the following. This is still a solution, and you didn't pay more. Yeah, I want to prove that, okay, I may have not used these vertices. So I want to say, okay, instead of deleting these guys, I'm deleting these guys. And I want to say this is still a solution to the node multi-way cut instance I have, and it's not paying more. Yeah, so I want to say that, okay, there are not more new guys than the old guys, and it's still a solution. Okay, good. So yeah, so we checked these two things. It's written here that we are not paying too much and that this is still a solution. And the second check, the second check is the same argumentation we had before. Yeah. Okay. If we actually, there's again now, okay, let's take, I don't know, this color, and if there's actually you undeleted this guy, and there is still, you undeleted this guy and you created a new path between the terminals, so there's some path between terminals, this path, but you deleted these guys. Yeah. So this path really needs to escape somewhere there. This path really needs to escape somewhere there for the guys like that you don't put into the solution back, that you don't put the solution back, because it needs to visit some other terminal than this T, because it connects to terminals. Okay. And then would you say, okay, but that means that this path goes there, but that means, but these guys were reachable from T even without touching the solution. Yeah, because that's how we defined this area. This area are the guys that are not reachable from the terminal once you deleted these guys inside this yellow area, inside this yellow area. Yeah. So if you need to escape there, that means that you actually could go from here to here, and there was a path between terminal T and some other terminal earlier, even in the solution. Yeah, I mean, it needs to be like be somewhere later, because you could have reached this guy from T even if with this guy is deleted here. Okay, so the check that the solution is simple, we need now to check that actually we are not paying more, Yeah, so I wrote here that this is actually this. This is a forward proof if somebody's interested. Slides are on the Moodle. But what I want to say now is that, hey, we want to say, hey, maybe actually you cut here, this is C and this is B. Maybe you actually cut more, this is larger than what we undeleted, that we created larger solution. Okay, so this part is larger than this one. Then I want to say the following. I want to say that in the LP solution, I could put epsilon here and subtract epsilon here. That I could shift a bit weight in the LP solution and we still be an LP solution. Okay, because okay, I decreased these guys by half. Okay, I decreased these guys by epsilon. And why these guys were important? Why these guys were important? Because these guys were important for the paths coming from T and going to some other terminal T prime. Yeah, because there were paths there were gas halves. So remember that the path is really hit if the path goes from terminal T1 to T2. It's hit by two halves on the way when the path leaves the zero region of T1 and when it enters the zero region of T2. It's cut by these two halves. Okay, and maybe this guy is the same vertex and then it gets one if this is like just two neighboring, if there's a vertex neighboring the two zero regions. Okay, so we only care about this guy decreasing its weight for the paths that start in T and go to some other terminal. Okay, because all the other paths are already taken for by the boundaries of the terminals leaving, entering, and leaving the corresponding vertex. But if you want to start from T and get to this vertex inside this reachable area UT, then you need to hit somebody from the solution B, because that's how we defined the part C that we are now deleting, which means that you're getting this epsilon back because you put weight there. Okay, and if there are less vertices here than here, then actually by subtracting epsilon here and taking epsilon here, you're actually saving. So our LP solution was not optimal. A contradiction. Okay, this is very similar in spirit to the vertex cover solution. It's just slightly more complicated. Okay, so this is our analysis. I mean, there's like stuff there. So we actually have the reduction that says, okay, so we actually have the reductions that you can actually find a half-integral solution and contract zero regions onto the terminal. Okay, and then check if there's another. I mean, you can also do the same poking around that we had for vertex cover. You can actually try to have a vertex like force it to be zero or force it to be one and see if you can extend the zero region somewhere there and contract as much as possible. And you also have got, if there's a vertex neighboring two terminals, you need to delete it. This is the analog of the edge connecting two terminals from the edge case. So you actually, yeah. So you can, yeah. So after you contract, so what you are already doing, you are contracting the zero regions, and then the guys where the LP put ones will be guys that are neighboring two terminals, because these two zero regions that are neighboring will be contracted onto the terminal. Okay, so the vertices that got one in the LP will become guys that neighbor two terminals and they're deleted. I mean, you can delete them. So you end up with this picture where the neighborhoods of the terminals are disjoint, and the unique optimum solution to the LP are just putting halves on the neighbors of the terminals. Period. Okay, and so that's what you can end up in this by applying this one. This is exactly, I mean, this is very similar picture when you get the vertex cover, that the unique LP solution is just halves on the neighbors of the terminals here, and that's it. Okay, so we end up with these pictures, and then we can do the same branching. We can either we apply this reduction successively, and then take a vertex adjacent to the terminal and branch into two subcases. Either take it into the solution and decrease the budget by 1, or not be in solution and contract U onto T, contract U onto the terminal. And the observation is that, okay, and then, yeah, I mean, you repeat the reduction rules up there. Okay, repeat the reactions up there. And the point is that you have the same analysis. So you have got the LP solution being a lower bound. So you look at the excess above the lower bound for your LP solution. When it gets negative, there's no solution because the LP is a lower bound from your solution size. And then in the branching case, okay, so you start with LP being at least half, because I mean the LP was a half approximation. Yeah, if you can always round up. So if the LP says less than k half or at most k half, you can just round out and say, okay, I solved it in polynomial time. This is the solution. Okay, so we can assume that the LP is larger than k half. So you can assume that so this potential is smaller than k half. Okay, okay, and we have got the branch when you delete the neighbor of the terminal. Okay, and the point is that because the unique LP solution was halves everywhere, deleting this vertex decreases LP by only half. Yeah, because this really corresponds to forcing this guy to be 1 in the LP. Yeah, so it's really like pumps up the LP by half, and then you delete this vertex and decrease by 1. So you have the same analysis in the vertex cover case. So this gap decreases by half, and yeah, this is like what's written here. Like this is exactly the same analysis as the vertex cover. Yeah, I mean, forcing deleting a vertex to be in the solution is really like forcing the LP value to be 1 here, which bumps up the LP by half, and then you decrease it by 1 and k by 1 by deleting the vertex there. And if you contract the U onto T, then you break the unique optimum LP solution, because this guy is contracted on T, is like forcing this guy to be 0 in the LP, which means that the LP goes up by half. Yeah, because this is like corresponding to forcing this guy to be half. So again, the LP gets down by half. So yep, so you have got this one. So we have got the potential is k half at the beginning, because we started with yeah, so we have got the algorithm that's like actually like 4 to the k minus opt LP. Okay, but this is at most k half. Otherwise, you have got a trivial solution. So this is 2 to the k algorithm for the node multiway cut. So we got the same solution. So we got the same running time bound, or the exponential part of the running time bound as for the edge case, but we needed to use LP instead of like the homebrew approximation by counting the minimum cuts between terminals. Okay, so this is it. And I want to mention here with these guys, before I go to the last part of the lecture, which I will do some outreach to some other things when you can use it, that you can actually, I mean, this is really like a branching algorithm. This branching algorithm is actually quite simple. You just branch on the vertex, but the reduction rules were quite complicated using LP, so that the branching reprogresses, and then you measure this branching in a quite non-trivial fashion. Okay, and there's actually a paper doing better analysis for edge multiway cut and doing some case mining for, and you can actually better running time bound. But to the best of my knowledge so far, this 2 to the k for node multiway cut is the best we know. So I don't know how we know how to prove the node things with LP seems to be more complicated here to improve it. Okay, so this is it for node multiway cut. Now I want to go and do some sort of outreach. This will be, I guess this will be quite heavy for some of you, in the sense that, okay, we did something familiar so far, and now we'll be entering some grounds that many of you may see for the first place. So treat this part as more like outreach, or like sightseeing part. So I want to say that, okay, so we said multiway cut. Where are more half integral LPs? And the answer is that there are not that many half integral LPs in theory, and we needed this half integrality, or like very strict structure, this half integrality persistence. But there's a different area when this thing pops up. This will be not really LPs. I mean, the LPs will be hidden somewhere there behind. The LPs will be still hidden somewhere behind this picture. We'll see them very briefly, but actually there's a better way of looking at these things than just LPs. So remember, this was our vertex cover LP. We had the vertices with zeros, less than half, half, more than half, and ones. And we have the proof that you can actually need zeros, halves, and ones for an optimal solution. Yeah. And what I want to say is that, like, this LP, it really says the following. Zeros are the guys don't take in the solution. Ones are the guys take into solutions. And halves are the guys I have no idea. Yeah. This half is not really half, is I have no idea. And this is a better perspective. So what I want to say is that actually, we ended up with all being halves by direction. The solution was able to take only zeros and ones. So what I want to say here is that actually, you think of the following. You have got take, not take, and I have no clue. Okay? So we depart from the like weights, zeros, halves, and ones, and the weights will be still there. But you think of the following. You want some polynomial time. This vertex cover LP was really a polynomial time routine that says these are the vertices you don't take in the solution, these are the vertices you take in the solution, and these are the vertices where you put joker, and I put joker, I have no clue what to do here. Okay. And what you really did here is that, hey, the vertex cover LP pays you 1 for every vertex it takes into the solution, but it pays you half for every vertex it says I don't know. Okay. And it optimizes this one. And it was like somewhat like one of the magical things here. What happened was that actually this polynomial time solvable problem, that you want the vertex cover and you can say I don't know, and you can say take, or you can say don't take, and you pay half for I don't know and 1 for take. Okay. That could be abstract at that moment. Let's go further. So we need a language to speak about this fix. And this is something which is called the valued constraint satisfaction problems. So that's what we want to generalize this vertex cover in the following things. Yeah. So you have got this is super like abstract slide, but you have got number of variables. You can think of nodes in the graph. Okay, you have got some variables. And these variables, every variable will get one of the, you want a value of the variable, and there is some like domain or alphabet, or it's sometimes called alphabet sigma. These are the values for the variables. Okay, these are the values for the variables, and the point is that there are something like constraints. Okay, there are constraints that says, hey, look at this at x1, x3, and x5. Okay, and looks at the values assigned to these guys and pay depending on which values do you assign there. Yeah, so this is like what's written here. Yeah, so I mean your instance in abstract form is like the number, a bunch of variables with some domains, and for some tuples of variables, like a table, how much you pay for different assignments to these variables, like for different tuples of assignments to these variables. Okay. And the important property here is that this is not a single problem. This is a family of problems, and like one problem is parameterized by how many elements you have in your domain, how many values you can have, and what type of tables of values you can use. I mean, what are like the patterns of like the tables of values you can use, and then the instance is a set of variables, and like to which tuples of variables you apply in which pattern of the like valuation pattern from the from your language. Okay, let's go for an example. This vertex cover, the vertex cover problem. Your language is for every vertex you have the value take this vertex or don't take this vertex. Okay, so there are two values in your there are two values in your sigma. Then in your instance, every vertex will be a variable. You want to take it or not. And now every edge will be a constraint saying that you pay 0 unless both endpoints are don't take, and then you pay plus infinity, which is like a prohibitive. You don't really want to do it because then the cost will be infinity. Okay, so for every edge you introduce a constraint saying hey, you pay 0 unless you take two empty balls, and that means that you pay infinity. Okay, and you put a constraint on every like single variable, on every single vertex saying, hey, pay 0 if this is guy not take, and pay 1 if this is guy take. Okay, and this is another formulation of vertex cover. Yeah, because the cost, the minimum cost of the solution is the minimum cost of the vertex cover, because you will never not take an endpoint of an edge because you will pay infinity, and then you minimize the number of guys you take into a solution, and you take the value you take the value the full bullet. Okay, so this evaluation, and yeah, and it's important to distinguish here that we define this one, and we define that you have got actually these two patterns for constraints, and then when you have a graph with vertex cover, you encode it as an instance of this CSP problem by applying F1 to every vertex and by applying F2 on every edge. Okay, so this is vertex cover, and the relaxed vertex cover, the LP relaxed vertex cover, is the thing when you also insert the joker into your domain. So a value can be joker, okay? And then you say, hey, it's okay, you can use joker, but you pay half for a joker. So every vertex will have got the F1 applied to it, which will say, hey, pay half for a joker, 1 for take and 0 for not take. And on every edge, you disallow taking to zeros, but you also disallow not taken joker. Not taken joker is also bad. This doesn't cover the edge. But you are fine with joker, and you are fine with joker and take. In particular, you're fine with joker and joker. That's the important part. Okay, so this is like our phrasing as a CSP. Okay, as phrasing as a CSP, what we did here. And why do I do so? Because now I can try to generalize it. Okay, and I will be using the following problem, which is in fact a very important problem in the theory of hardness of approximation algorithms, which I don't want to dive into. But this is a problem. Let's look at the following problem. This is a variant. I mean, this is a special case of the unique of the. It's like a special category of valued CSP problems. Okay, and what you're doing here is that every vertex has got its alphabet. I mean, it's like domain, okay? And there's a graph where on every edge you have got some permutation, okay? Every edge is some permutation that says how the color, I mean the color, like the value on this variable should translate to a value on this variable, or you can take the inverse of this permutation and translate it the other way around. Yeah. So on every edge inside the graph, so the variables are vertices of the graph. Now every edge you have got a constraint how a color on one endpoint should translate to a color on the other endpoint. Like the value on one endpoint should translate to a value on the other endpoint, and in the other way around, it needs to be bijection. So there needs to be like one-to-one properties. Okay. So this is this was, and now okay, if somebody asks you to color to like make an assignment that satisfies all the constraints, have got cost 0, okay, satisfies all the constraints, then it's easy because you guess the color of one vertex and then propagate across the connected component and check if everything fits. That's easy, but the difficult part is that okay, we want to break at most k constraints, and can you do it? And then the problem becomes a bit hard. Okay, that's the difficult problem. And now we want to like understand what's like with the property of this, with the properties of this problem. So we want to understand, okay, what can we the properties of this problem. So yeah, so this is the problem. And now, okay, so this, for example, a solution to this instance with only one guy, which only one violated constraint. So one constraint. So you can think of this constraint paying 1 if it's not satisfied and paying 0 if it's satisfied. Okay, if this is the permutation is respected. Okay, so this is a solution that violates only one constraint here in this picture. Okay, so this is, as I say, our valued CSP. The alphabet sigma is like the domain, the colors, and for any permutation, there's a constraint that gives 0 if the permutation is happy and 1 if the permutation is unhappy on that edge. Okay, and you can have a relaxation here. Okay, and now this is like the important thing which I will like sketch over here. Let's do the same relaxation we did for vertex cover here, namely add I don't know to the alphabet. Namely, okay, we add also, apart from the colors, like the values, we add the value I don't know. We add a joker, and we say that placing a joker costs half. you cannot place a joker. I mean, you placing a joker costs half, but an edge with two jokers is happy, and an edge with a joker and any color is costs half. This half might be a counterintuitive. It's something that works in the algebra later, so I don't want to like focus on that. Okay, so you are relaxing the problem. We are allowing putting jokers on vertices, but the joker pays half, and an edge between a joker and a non-joker pays half as well. Okay, so the boundary between jokers and non-jokers pays half. Okay, so like the constraint is like half unhappy if it has a joker on one side, and the constraint between two jokers is happy. Okay, and the punchline is that actually this I put a question, but what we'll be discussing in a moment is actually this one is polynomial time solvable and has got the persistence properties we want. It has got the persistence properties that okay, if something is fixed, we can fix this value up there, which is something we are going to use for the algorithm. Okay, but let me sketch from where this I mean, this can be super abstract for you that actually this type of relaxation turns out to be polynomial time solvable, but I want now to highlight that there's actually a deep reason for that. Okay, so actually highlight, and this really boils down to a work from 7 years ago of Tapper and Zhivne that says that value CSPs are NP hard or they're polynomial time solvable. But if they're polynomial solvable, there's the canonical way of solving them. There's a very natural way of like writing an LP. I write the LP like like for every variable and for every variable of the CSP and for every value you take a variable to what extent this variable has got this value, and you write the LP and you just do like the natural thing there. And it turns out that actually the value this is the canonical way of solving it. I mean, if the problem is polynomial time solvable, then actually this algorithm will always find the optimal solution, integral optimal solution, and this is like the way of solving it. Okay, this is the theorem we are not going into. This is a very deep work from a few years back. The point is that this is polynomial time solvable if all constraints are something which is called S submodular. This will resemble submodularity from cuts. I mean, it actually comes from the name comes from the cuts because you can phrase the cuts as the submodularity in these ones. But there's like some special case of constraints which are called a submodular, which always give a polynomial time solvable valued CSP. And that submodular is a case where you have got a constraint where the domain has a joker. So there's one designated value of the domain where the value is called we call it a joker. I mean, let's call it a joker here. Okay. And there are two operations which correspond to like set union and set intersection. Okay, so you think of, instead of thinking of sets, you think of like joker means not in the set, and color means, I mean, you are putting in a few different sets like green set, red set, blue set. Okay, and then you are taking intersections or unions of the sets. Okay, and the point is that, okay, something outside the set will be always outside the set. If something is outside one set but inside the other set, it will be not in the intersection, but it will be in the union. Okay, this is like what's written here as well. Okay, if something is in the same set, in the red set here, in the red set here, it will be in the red set, in the intersection, the union. But if something is in two different sets, then it will be in neither of the sets, in both intersection and the union. Okay, you cannot like sum up to, if the element belongs to different set, there is a conflict, and you just say he's nowhere in the intersection and the union. Okay, this is usually not called intersection the union. It's usually called a bit different, but let's call it intersection the union. And you can think of these guys as like operations coordinate-wise. If you have got a long vector of values, like a function, then you just apply coordinate-wise this operation. That's like the intersection the union. Like this, you can think of like this is like on a single vertex. So like you can, if you have got a function with values in the domain, you apply coordinate-wise the operations intersection the union. And the submodularity means that I mean the same algebraic sentence as it was before. I mean, if you have got to if you, I mean, you think of this as a valuation, like how much you pay for a tuple, okay, and you have got one valuation, another valuation, and you take these valuations, you hit them with intersection, and you hit them with the union, then you pay for the intersection, the union, not more than you paid for the original valuations. Okay, and the point is that our relaxation from a few slides back of the unique label cover is submodular in this sense. Okay, is submodular in the sense, and that's the underlying reason why we put halves on the, I mean, this halves between on edges between jokers and no jokers. That was necessary to take submodular, but this is like what we get, and there's actually like so actually this gives us the fact that relax unique label curve is in polynomial time solvable, because this constraints I didn't check it too. I just doing a like overview sketchy thing here. But you can check by hand if you're bored through the Christmas, that actually this permutation constraint is submodular by this definition. This is a tedious but not very scary check. The point is that for branching algorithms, we also needed the persistence. Yeah, we need this property that if we get a relax ULC instance, and if the relax solution gave a color, non a joker, that gave a value to some vertex, we can actually fix this value. We can fix this value and like don't worry about it any longer. And there is a very magic observation, which I admittedly I don't understand where it comes from, but there's a proof. This is the proof saying that if you are submodular, you also have got persistence. And this is like hitting. I mean, this is like algebra, magic algebra for me. I don't have any intuition. I'm not an expert in valued CSP, so I don't have any intuition here. So I don't want to go over these calculations with you because that won't be insightful. But the magic thing is that with persistence, you have got the fact that if you have got submodular, then you also for free get the persistence, because I can actually quite easily prove. This is the proof. I'm not going to go over it in details. That actually, if you have got a fractional solution, this is the fractional solution, and if you have got the integral solution, then you can actually hit it. I mean, you can use persistence to show that actually you can replace the integral solution with the integral solution twice union with the fractional solution. And this array says that if you hit something twice with the union, you actually replace the integral part with the one from the fractional. Okay, you say that in this operation we took the integral one and we replaced the integral part from the fractional optimum solution gets replaced up there by hitting twice with the union, and the similarity gives you that it actually you won't pay more like this one. Okay, so this is the proof here. So you can do the branching algorithm, yeah? As long as there exists a solution to relax ULC where that doesn't use all jokers, then you fix something and reduce. You can actually quite easily reduce, and you can add some unary constraints which are also some modular to say that to restrict some values and remember some things, some boundary conditions up there. Okay, and once you get to the point when all jokers is the unique solution, to the relax optimum, to the relaxed thing, which corresponds to like all halves in the vertex cover case, then you branch. And you have got sigma choices because you take this guy and assign one of the like sigma values to it, okay? And the point is that the relaxed optimum goes up by half in each choice. And this is your gain. So your lower bound, your relaxed LP goes up by half, and then you do some reductions and reduce up there. Yeah. And this was observed by Magnus Wallström a few years back, and this gives you an algorithm of running time sigma to the 2k. Yeah, because I mean you decrease the budget. The budget k is by k by 1. I mean the cut size is cut size by 1, and you decrease it like you can decrease it 2k times, and each step you have got sigma branching factor up there. Okay. During the tutorials, I hope Wojtek will be doing something. It's relatively easy to phrase edge bipartization and some other edge deletion problems, a few edge deletion problems as unique label cover. So you may have some like occasion to familiarize yourself with this quite abstract notion of this problem. Okay, I want to say that also Magnus in his work said that actually there you can have, apart from this constraint, you can have constraints like these guys are equal or pay 1, and this allows you to generalize things to vertex deletion problems, because the previous one is really about edge deletions, like violating these edges. It's not easy to get vertex deletion problems, but you can actually extend it to some vertex deletion problems. It's sketchy up there. So actually, like the vertex deletion has got also the same running time bound. Okay, And tapejivne won't apply directly, but you can circumvent it. And you can solve unique Lepie cover. There's another problem which is called group feedback vertex set, which is a full generalization feedback vertex set, which also gets a nice problem, nice algorithm with this framework. But I don't want to even define this problem. And I think that's it. And wow, it's exactly the end of the lecture. So thanks. I know that it was heavy. I mean, I started with something easy today and gradually made it harder and harder. So please treat the last 20 minutes of Unicable cover as an outreach, what you can go in these directions. And I'm stopping here. Are there any questions to the content of this ones? Or I don't see questions. I'm stopping the recording.